So, jag tänkte, this lecture is going to be about two things. So the first thing is I'm going just to give you some details on the final project assignment, and also what kind of the structure will be on the final presentation. So let's see here. Some important dates here. So you will get the final comments on your assignment 5 today. I think some of you already gotten some comments. Tomorrow I will send out table showing the group assignments for your peer assessments, which will be done at the final presentation. The final date for the project turn-in is on the 29th of May. At that same point, there will be a separate turn-in for to your assessment group. So that will be available at that time as well. And on the, let's see, so I say correct, on the 5th of June, there will be a final project presentation. And this will be, of course, conducted via Zoom. So we'll try to arrange that every group can present via Zoom. So the idea is that every group will present their program, any special features you have in your program, and show it running for the entire group. That will take, you will get something like 10 minutes to present your program. Then there you have the peer group will have 5 minutes to comment on your code, your report, and the running of your program. And then the other ideas they have on improvements or what was really good about your project. So these are important dates now. There will be some exercises uploaded then where you can ask more questions and work on your final project as well. So the final project, at that point, on the 29th of May, all comments in the submissions must be corrected, or we probably have already done this, but you should kind of have solved any open issues with your program at that point. At that point, we will also require you to turn in a report that kind of comes with your program. So the project should contain a description of your problem area, or program, and briefly on the theory. You don't have to do any big theory description with a lot of formulas, just kind of the basic, but what kind of theory the application uses. You should describe how you have structured your program. So if you have structured in different modules, you should kind of explain that, and also if you have some other structure that is relevant to your design of your code. You also need to do some kind of, the comparison controls you did early on should also be turned in now. They don't have to be on the large problem, it can be on the small problem as well. You should also give a kind of assessment of the correctness of your calculation. To kind of give a kind of a short reasoning on how do you perceive that your calculations are working. So perhaps with a hand calculation or kind of reasonable discussion on the results. You also need to provide a manual with examples how to use your program. Perhaps with examples on the how you should kind of click in your program, so that your peer assessment group also can understand how to run your code. There should be an appendix with all the source code, and also not part of the report, but a zip file with all your code, your input files, your UI files, any other files that are needed to be able to run the program. This is also what you're going to share with your fellow students, so you can they can run your code as well. The peer assessment should be comment on the readability and structure of your report, the structure of the code, any kind of comments you have on why they have structured the code, or good things you think you should on the code that you have that you're reviewing. Comments on the user interface, how well it works. Are there any problems you see, or both positive and negative? So it shouldn't be just negative comments here. So you should also kind of comments on the good things of the user interface. Usability. So I mean, did it run? Could you kind of take the code and run it on your computer? And it shouldn't be super large. So kind of maximum of a page of comments, even less, but kind of reasonable. So you don't have to comment every spelling mistake in the report, but on a high level. So some of the criteria for getting a Godkänt in this course. We must be able to run your application with the instruction from the report. So that's really important. So it has to be able to run. You should also be able to open an input file, which you should provide in the final project, and execute a calculation. That's kind of the basic criteria for a computational program. You should also be able to save your input data for your program to an input file. And you'll also have to be able to read it back from that input file and run the calculation again. The visualization windows should be working. The parameter study should be able to be executed, and the VTK file should work in ParaView. For the final one here, I'm kind of, because of the many problems we have with ParaView here, but you should be able to write VTK files, and the parameter study should be able to execute and write the VTK files. If you can't create images for the VTK, it's okay with me, but it should be able to run at least the parameter study. So that kind of is for the project assignment. So I'm kind of open for questions now. So if anybody has any questions on the final report and the following weeks here, what's to be done, feel free to ask questions now. Don't forget to unmute if you have a question. So.
I have a question about comparative calculations in MATLAB.
Yeah.
So should we just take an example from the program and just do the same thing in MATLAB and compare results, or?
Yes, that's it. Just to see that your code computes the same as the MATLAB code, similar code, so that you did it from the beginning.
Okay, can we just attach the one from the beginning, or do we need to make a new one?
No, you can just attach separate source code files for that, so it's you don't have to make new ones.
Okay, thanks.
Okay. And I have a question here on the theory should cover the calculation and the theory of how the code works. So, I mean, the theory of what kind of problem theory you're using for your code. And the theory on how the code works is more, it's kind of the same. So basically what kind of finite elements you're using, what kind of models you are using in theory in those elements. But not, and then you describe how your code works in the structure of the report. So you have a section that describes the structure of your code. But then you have a section that describes you're studying temperature or stress, and kind of a brief overview of the criteria for the criteria. So what problem area you're studying. But you don't have to do a lot of formulas, just kind of a brief description on what the basic assumptions of your calculations are. And of course, you're welcome. If you have any questions before that, just send me an email or send me a message from through Canvas, and I will try to answer that as soon as possible. And also, if you need to kind of do a Zoom session, just ask me, and I'll set up a Zoom session for you outside. There's a question about the documentation on the code. You can provide, so if you generate documentation using a tool called Sphinx, you can provide that separately. But you should provide a kind of appendix with your code as well. I think you can generate a report in Sphinx as well. But, okay. So I continue now here with my other presentation here, and if you have any question, we can follow up after my next lecture here. So there will be some time over for that. So my next part here, I'm going to talk a little bit about high performance computing. So your code is using a library called NumPy and also SciPy in some sense. NumPy and SciPy are highly efficient ways of computing with matrices and arrays. And it's very, so at some point when you have designed your simulation code, you probably feel that, okay, this is too large to run on a normal computer. So you probably start looking for larger resources. And this is what I'm going to talk a bit about today. So in addition to teaching structural mechanics and programming, I'm also the director of LUNARC, which is the Center for Scientific and Technical Computing at Lund University, where we provide researchers with resources to run larger problems, basically. Large computers that can run larger problems. And Python is, Python code you have written is can be run quite easily on these machines. Because Python is platform independent, so you can run them on a Mac, you can run them on a Windows machine, and you can run them on supercomputers. So I will give a short description of high performance computing, what it is, and yeah, so you get kind of an overview what this area is. So what is high performance computing? So it's a broad term for the fastest computers currently available. They can be used for example, number crunching, scientific simulations, analysis of geological data, computational fluid dynamics, structural mechanics, and many areas that you get problems that kind of really quickly become complex. So another explanation is that it's kind of time dependent. So a supercomputer 10 years ago is like your laptop, or kind of today. So it's kind of very time dependent. But one kind of quote is that it is a computer that offers much greater capacity than your desktop computer offers at present. So when you grow out of your laptop or desktop, the next step is kind of larger servers, more cores, more CPUs, and then you quickly get into the supercomputers. Supercomputer can also be something that can have properties that normal computers, computer architecture doesn't offer. So for example, if you have problems that require significantly large amounts of memory, that is something that can't be handled by using a single computer, because of connecting in multiple ways to kind of create a large memory area. That is also can also be a supercomputer. So why do we need supercomputers? I mean, many of you think that computer development is fast enough, and next year you have a computer that's much faster than today. But the problem is that there are problems today that require large resources today, and we need to solve them today. And also, faster computers also have the ability to make more simulations. So, for example, you want to do crash tests, you want to do multiple of these, and as you said, you have done a parameter study to study, for example, what happens if I change a parameter, and you can't wait 2 months for computations to finish. So, by having a supercomputer, you can finish those parameter studies much faster because you can run them in parallel. And also, faster computer can provide the ability to make simulations faster. For example, weather predictions. You can't wait for a supercomputer for 2 months to calculate the weather today. For this kind of task, you need a computer that can do that today. So an example is in meteorology, where you need to kind of do weather simulations. And how accurate you can do the simulations depends on kind of how fast your computer can be and how large it can be, because you divide your area into smaller areas, and the smaller areas you have, the more computational complex the problem becomes. And that is done by supercomputers. So today, I think in Linköping there is one computer which is synchronized with a computer at SMHI, which is also synchronized with a computer in Norway to kind of provide the weather simulations for Sweden. Crash simulations is also something that is extremely expensive to do in the real world. So you want to do, before you do the real test, you need to kind of do a lot of simulations of this. And these are also computationally expensive and can be greatly you can finish more of them and also do them faster by using a supercomputer with multiple using a supercomputer. Fluid simulations is also something that is extremely computationally expensive, especially if you want to resolve finer details of simulations. So every time you kind of make the computational mesh finer, the more calculations you have to do. And supercomputers can kind of reduce the time to kind of get to results with these kind of calculations. At LUNAC, we also have a lot of new research groups that are getting more and more data that needs to be analyzed. And in medicine, it's also something that is, so they can analyze larger data sets by dividing these data sets and having multiple servers analyze the data simultaneously. Structural mechanics, you can have quite complex models here. And the left side here is the first image is actually a photograph of a section of a tree or a wood where you want to make paper pulp. So you want to grind it to paper. And this process is quite energy intensive, and you want to know how it works. So the image in the middle here is examples from a finite element simulation to study how you break up this wood structure. And there is a metal plate forming is also very computationally expensive, and there you can benefit having large computer resources. Chemistry, there's a lot of where you do simulations on chemical processes down to the atomic level, and a large portion of our computers at LUNARC, they are running chemistry simulations all the time. They are very good in scaling as well, so they can quite easily scale up to many servers to run in parallel. So a little history here. So you usually measure performance of supercomputers by the number of floating point operations per second. So it's called a flop. So a floating point operation is a flop, and then you can put some SI units before them. So you can have, for example, megaflops, that is million floating point operations per second. And in 1964, the largest computers was the CDC 600, and it did 9 megaflops. So today you have, I think this should be increased to at least, so 3 gigahertz PC today is something like 24 gigaflops or something. So it's much larger. This is a 2-core machine. That means that you can have 2 cores running simultaneously, then you get 2 floating point operations per core. That means 6 gigaflops performance. So you see that computers at the time in the 60s were quite large. This here is actually not the computers. These are actually the storage. So these are tape storage. So all the computer programs were stored on tape. Then the result were printed on a printer. And this is actually the computer here. So those large racks here are the computers. And this is actually a lecture here. You had a terminal with a CRT tubes here, which is kind of oddity for the 60s. Most of the input was done on teletype machines where you had a printer and a type where you typed into the and printed on the paper directly. So let's see if we continue here. So in '69 we had a Cray CDC 7600. We were up to 40 megaflops. Still large rooms here with a lot of tape storage. In 1976 we had the Cray 1, and now we're up to 160 megaflops. And this was just the compute unit here, we see here. So it was nicely designed with a way you can sit around it here. It was a single processor that could do a lot of vector operations. In Sweden, we had a Cray also in the 80s, where we did a lot of the calculation or early calculation for both Viggen and JAWS. It was highly protected because the Americans really didn't trust Sweden at the time. So it was kind of locked in, and there was a lot of security around that computer. Cray XMP, 235 megaflops. By the way, Cray is one of the only supercomputer manufacturers that's still around today. So there is a Cray in Stockholm. It doesn't look like this anymore. It looks more a normal computer. In 1986, we had IBM 3090 VPF, and that stands for Vector Processing Facility. This was the first computer we had at Lund University, a supercomputer, and it did 110 megaflops. And Vector Processing Facility meant that this was a single CPU, but it could work on vectors in parallel. So you can compute long vectors and vector addition multiplications in single operations. So it was a vector supercomputer. In 1999, we were starting to kind of close into the PC performance now. So now we have 2,144 megaflops. And then in 93, we kind of surpassed the standard PC now. So now we're at 13.7 gigaflops in the computer. These computers were really expensive at the time. And usually they came with a dedicated service operator as well. So there was a technician that could repair these, because they weren't standard computers at all. They were kind of highly specialized computers built for one purpose. And so they needed specialized technicians to be able to operate them. In '97, there was a shift in kind of how you build computers. So ASCI Red was one of the first supercomputers built on standard server hardware and also based on the Linux operating system. So now you took kind of what was available in computer rooms and put them together and used Linux as the operating system in a large supercomputer. So now we're up in 2.38 teraflops. In 2002, Japan did one of the world's largest machines, at least area-wise, to simulate a lot of their weather simulations. It was 35.6 teraflops. And you can see here, this is a view from the control room, and you can see all the racks for this computer. 2004, we had Red Storm, a large machine in the US. This was a kind of interesting machine. You see it has different colors here. You have black, you have white, and you have red. And the black was actually for the military, and it had an ability to automatically separate the black parts from the white parts here. But the white parts in the middle was kind of flexible, so you could resize the black parts and the red parts in different ways here. In 2005, 2007, IBM did a large research and development in a new architecture called Blue Gene, which was smaller processors, but a lot of them. And this is the Blue Gene architecture. And this part here, the reason it's skewed is because it's cool from the side. So they blow cool air in from the side here, through here, and push it through the racks like this. So this is also, these machines are extremely power hungry. And power means heat. And you need, when you produce a lot of heat, you need to be able to remove the heat in an efficient way. Otherwise, these machines will burn. So cooling of these machines is a really important aspect. So now we're back in Lund. So this is the Alarik machine we got in 2012. Lunac has been operating since 1986, so this is just one of our computers. We have multiple computers before that, but in Alarik we were at 40 teraflops. So you can see here, if we go back to the Earth simulator, was 35.6 teraflops in 2002. In 10 years, we could house the same performance in just a couple of racks. So these are racks here. So in this here is a compute rack. So here is servers that are stacked on top of each other, and between these racks there is a cooling rack, and then there's another rack. So it's cooled from water cooled, and this blows cool air in the front of the servers, and it sucks the warm air from the behind again and cools it back. So it's kind of sealed air cooled, but with the water cooling in between. In 2008, we broke the Petaflop range here, and this is a modern version of a Cray. And these are the computing racks. So these are about 2 meters high, and they're just stacked after each other here. All of this here on the top here, these are cooling hubs. So that removes the cooling, and then there's a heat exchanger here. So you see that this is kind of cooling is expensive in these machines, and it's also really hard to do efficiently. You see also this is a quite it's almost like a football field in size, so it's large. In 2008-2009, IBM introduced the Roadrunner system. It was up to 1.7 petaflops. In 2016, we at Lund University got Aurora, which was a 240 teraflop machine. And we expect probably during next year to ourselves break the petaflop range. And when you have these cool computers, you need to be able to do cool lighting effects here, so they look kind of nice. So we actually have a LED lighting here in this to simulate an Aurora. In 2018, we visited the Texas Advanced Computing Center, and they have a machine called Stampede, Stampede 2, which is actually 19 petaflops. And in the coming years, we will probably also breach the exaflop range. So there is a lot of initiatives in Europe to build exaflop machines, and there is one machine being built in Finland called Lumi, which will exceed probably, hopefully in 3-4 years, the exaflop limit as well. So how does this architecture work? So there are a lot of parallel computer architectures that can be used. And if you have a single computer that can execute one instruction per cycle, it's called a von Neumann machine, or a single instruction, single data. So the computer processor processes one data at a time. There is also what's called SIMD, which is single instruction, multiple data. That is what I showed you before with a Lund University machine, the vector machine, that can work. So single instruction working on multiple data. So it can process arrays and vectors. There is no machine called multiple instruction, single data. So that's kind of a mute concept. But you have multiple instruction, multiple data. So this is what the situation is today. And if you look at supercomputers today, they are kind of a mix of both many servers, but also inside the servers, there's an architecture where you have multiple CPUs running in the same memory space. That is called multiprocessors, where you have processors running inside the same memory area. So you have, if you look at many computers where you buy today, they have 4 cores, 8 cores. These cores are basically a small processor. So every computer today has multiple processors, but they have the same memory. So they work in the same memory. Compute cluster is the where you have, it's called multi-computers, where you have multiple servers with smaller processors inside, where you connect them together using a network to build a larger compute cluster. And those clusters, they communicate using message passing. So these are the two main designs. So this is what you have in your normal laptop. Perhaps that's not as many processors as you have here. You have a shared memory here in the middle. So all the processors can access this memory and work on this memory at the same time. You need, of course, to synchronize access so they don't write on the same memory at the same time. But this is the idea. This is the when you build clusters, you take a lot of these machines here where you have a processor and memory, and then you connect them together in a network. So in this case here, if this processor here needs memory here, it sends a message over the network here and asks this processor to provide the memory here. So it sends messages over this network. And as networks are getting faster and faster, this is a viable solution. So you buy a lot of servers, you connect them together, and you can having 2 servers, you get twice the memory and twice the number of processors, and so on. So if you have 4, you have 4 times the performance. The only bottleneck is the network here. So if you have too many processors, the network can be kind of congested, and that becomes the bottleneck of your computations. The network can be arranged in many different ways. You can have all the nodes connected in a star, so they can connect together here in different ways. You can have networks where you have connections from all to all, so one node can access multiple nodes like this. You can have a tree-like structure, so if you're a node here and you want to communicate to this node, you have to go up the tree and back down again to this node here to communicate. So if you want to communicate to this node, it's just up and down. This is a very cost-effective network, but you can get congestions here when you have much communications on the top. Then you can have cube-like and 3-dimensional cubes like this to enable efficient communication from multiple points at the same time. So what happens when you have these computers? So what you want to happen is when you add servers to your supercomputer is that the more servers you add to a problem, the faster it goes. So in this case, this is a typical diagram you often have when you compare different problem types. So for example, if you have an n-body problem like a particle system, if you add CPUs on the bottom here, the speed is almost linear. So this is the ideal solution when you have a linear speed up. So if you have 40 CPUs, you get 40 times the speed up. But this is often not possible due to network and communication issues, but also your algorithm can have problems. So for example, this is a more reasonable scaling perhaps, that it kind of teeters off a bit. But if you have scaling like this here, the bottom line here, so when you go like this, then it's, so for example, after 10 processors, there's no use to kind of adding more processors to the problem. It kind of just stops. And when you have these kind of figures, you need to kind of probably rethink your algorithms. Could be that you have things that are too costly, you have to communicate too much, or you have to reduce, think about how you design your algorithms in different ways. So this is something that is not useful on a big machine. Then you need to kind of look at your code. So network, so that is an important component of a supercomputer, and it's one important aspect is how much you can communicate, the bandwidth. That is kind of how many megabytes, gigabytes per second you can push, or terabytes per second you can push over the network. But there is also another factor that's really important when you have large parallel programs. Sometimes it's not important the bandwidth, but you want to communicate really fast and let other processes know when something has finished. And you don't want too big delays there. And that is called latency. So it's the kind of time for it takes to initiate the communication. And that is an important factor when you design the networks for supercomputers. And it's the choice of a network is kind of depending on what applications you have. If you have, for example, a movie studio that needs to render a large movie, that can be done very easily by dividing up the frames so one computer does 10 frames, the next one, the next 20, and that scales highly parallel. And you don't really need a fast network between the computers to handle the synchronization of this. But there are other simulations, for example, structural mechanics, where you need to communicate a lot on the simulation state between each step. Then all the servers in this computation need to be synchronized. In normal computing, you have a gigabit Ethernet, and you have like 1 gigabit, 10 gigabit, 40 gigabits, and 100 gigabit Ethernet standards. It's kind of cheap, and it's not very expensive, but it has a high latency. So, and to kind of come over that, there is for high performance computing, there is a special infrastructure called InfiniBand, which is a special standard that has a lot of, it can communicate without interfering with the processor. So it offloads the processor and also has very, very low latency. The computers at Lunarx have had all the kind of, so we started with building really off-the-shelf computers with 100 megabits Ethernet a couple of years ago, moving to gigabit, and then currently we are using InfiniBand with 56 gigabit connections. And the next cluster will probably have 100 gigabits and higher bandwidth between the compute servers. This is just the latency here. You can see that gigabit Ethernet has a latency up to 120 microseconds, and InfiniBand is 1.26. So it's an order of magnitude faster to initiate communications between servers. So a couple of years ago, when you bought a supercomputer, you bought kind of one supercomputer, big resource. It was really expensive, quite a lot of resources, and only a few centers around the world could kind of afford these machines. Something that happened between in the 90s is that the PC became available, and it was mass produced. And that means that the PC architecture today became a mass market, and also the components were really low cost. So What happens in the 90s was that some researchers thought, okay, but why do we have to spend so much money on supercomputers when we can build them ourselves? So in 1993, Donald Becker and Thomas Sterling, they kind of had an idea. Why don't we take a number of PCs, put them in a box, and connect them with a network, and build our own supercomputer? So they took 16 PCs. It was 486 Intel 486 processors, bought them in the local computer store, and connected them together. And what enabled them to do this was that at the time, Linux was becoming popular. It was free. So basically, you can build your own, how many computers you wanted without any licensing costs. Another important aspect is that there were free compilers. So compilers that can take your C code and compile that to this architecture. And the third component of this was a standard way of communicating in parallel programming with messages. This standard was called MPI, and that was open source and could be kind of integrated in the system. So by using this technology, they built a really cheap cluster or supercomputer. And basically, all the supercomputers today use this architecture. So the supercomputers as Lunark is just a bunch of Linux servers connected together in a network, and we have a queuing system that controls the access to this and the communicate over a InfiniBand network. But basically, it's the same architecture that Donald and Thomas Sterling created in early '93. So Beowulf and also the commodity of the shelf concept here enable cost-effective computer building. And the nice thing is you just choose the components you need. So if you don't need a fast network, don't buy a fast network. You buy a kind of what is needed for your application. Also, you can choose from many suppliers, processors, memory components. There are some negative aspects of this. There are not so many today, but there are some though. It's really hard to build supercomputers that have a lot of processors using the same memory, because you can buy a lot of machines. The memory is private for each server, so you need to communicate between them. And in some kind of problems, it's more important to be able to have the processors near the memory. And some of these network architecture behind this machine can be really expensive. So if you want a really fast network, the network cost can be really high. And also, because it's commodity of the shelf components, you can have higher failure rates on the components themselves. So, but usually you design that into the cluster so you can cope with a couple of servers being down for maintenance without any problems. This is just there is an organization called Top 500 that collects statistics of all the supercomputers in the world. And they also collect statistics on the evaluation of how the technologies evolve over time. So you can see here, this is a timeline from 95 up to today. And if you look at 95, there was a large section of single processor supercomputers. And SMP, that means shared memory processor. So that is shared memory machines, basically one single machine with a large memory and multiple processors running inside. MPP, this is the kind of classic cluster we have today, precursor to that. And then we also have SIMD machines, single instruction multiple data, basically vector machines here on the top here. But what we can see here is that MPP and cluster, this is the classic Linux cluster. It started here in the 90s, really small, and it kind of grew here. And now you see we have the entire section here is clusters, that is Linux clusters. And then we have some specialized machines here on the top here. Then we can also see the operating systems here. So if we start in 95, we had Unix. This is not Linux. This is Unix. This came from the from Berkeley, the University of Berkeley, and it was a kind of a not open source system, but it, you can ask for a license. You can use it on your own computers, and that was used very much in the beginning here. So you see here, over 100% was kind of Unix based, and you can see here in the 90s, mid 90s here, you have this red one here, which is Linux, and you see here it has grown with the cluster usage as well. So today, every cluster is superconductor, even if it's proprietary and none of us are proprietary architecture, are running Linux as the operating system. Here you can see, let's see here. I think this is. I just can't see the title here. Oh, yeah, this is a number of cores per socket. So this is the number of cores you have in your processor. So you can see here in the beginning here you had 1, and then you had the gray one is 2, and then you have 6 and so on. So you can see the share of cores per socket. And today we have up to 24 cores per machine. I think AMD now has 32 cores per processor. So if you buy a server with 2 processors, you can have 64. They have up to 128 CPUs in a single machine, which is quite good for performance. Here you also can see different accelerators. So today you also put a special accelerator card in your computers, basically a graphics card to do highly parallel workloads. And the dominant player today is NVIDIA. So it's orange part here. So this is the normal no accelerator, and you see here that it's growing here. You add accelerators to your computer. This is the network architectures development. So in the beginning you had specialized networks, these blue ones here. You also have, today you have gigabit Ethernet, InfiniBand. This is the InfiniBand part here. You have gigabit Ethernet, and you have custom interconnects here. So the normal way of building clusters is either gigabit Ethernet or InfiniBand. Then there are special clusters with like Cray, which have their own networks here. This is the red part here. Here you can see a chart here of the total. So the green line here, this here is the sum of all performance today. So you see, if you sum all the computers today, we are at exaflop limit. The top 500 computers are the triangles here. So these are the fastest computers today. And the blue ones are the kind of lower level of the top 500 list. So you can see here that we are at 230 teraflops. We are somewhere like here. So you can see the development here. And you can hint there is a kind of flattening of the curve here. That is due to the fact that it's really hard to add a lot of things on the processors today. So it's actually, you can also see that the clock frequencies hasn't increased a lot over the years. The density of the cores has been increased, and it has been harder each year to kind of double the performance. So how do you use clusters? So the main way of using a cluster today is you log in with a terminal or a remote desktop. And there you find all the software and compilers you need. There is a shared file system between all the servers and the front-end machines, and you upload the files to this login machine. And the access to the servers are controlled using a queuing system. So basically, you define your job in a script. You send this job to a queuing system, and then the queuing system kind of assigns your job to certain servers in the cluster. And it also kind of determines when you're able to run at the best time and when there are resources available. So it works like a scheduler or a calendar. So you have a queue of jobs coming in here. They can be different. So this is a two-way job. It's 2 processors long. This is a single processor, and this is a single processor, but they have different length. And the scheduler's task is to kind of put these jobs into the machine in the most efficient way as possible. It could be that the red one goes in front of them and the other ones have to wait. So the scheduler's job is to kind of divide this in the most fair way as possible. So the trends today is more cores per processor, but at the same time it makes it hard to use because it's very hard to use all these small processors in an efficient way. When you're using NumPy, for example, if you have 4 cores, it will try to use all these 4 cores at the same time when you're doing matrix calculations. So if you solve an equation system, if it's large enough, it divides all these to several threads in your computer, so it uses all of them at the same time. Something that has been developing in the couple of years now is using GPUs for computing. So a graphics card today, when you're playing games, it has thousands of small cores. These are highly specialized processors that are limited in some sense, but quite complex in other sense. So you can actually do a lot of complicated computations at the same time. And that is used in machine learning and AI today, for example, using these GPUs to do very many calculations at the same time. They are not as easy to program as NumPy, for example. They're a bit more complicated, and not all problems you can work into this hardware. So just to show a little bit, this is a blade server on a Aurora machine. So this is a single server here, and there are 8 servers here, and there is 8 servers here. So, and this is approximately 10U high, so it's like half a meter high. So in this area here, you have 384 processors that can run simultaneously. Each of the servers have also a hard drive for scratch operation. So basically, it's complete computer in each of these modules here. This is a Tesla compute node. And here you have a normal processor here. This is a normal processor, and here you have a graphics card connected to them. So this is a processor, and this is a GPU. Processor and GPU. Just to give a very quick tour of the computers we have here in our system. So this is the way Lunark looked when I started to work at Lunark. So we built Linux clusters. And basically, we put a lot of computers, put them on shelves, connect them together with a network, really handcrafted networks. But basically, these were normal desktop machines connected together using a standard commodity off-the-shelf switch. Next cluster we built, we realized that we should perhaps have a bit more compact machines. So we bought Dell small form factor PCs and connected them together. Then we got more high density on our compute racks, more networking. to excuse us here, this computer was moved once, so we couldn't get the cables really nice here. So that's why you see this big hive of cables. Next, we built a grid machine for the high-energy physics community, and now this is the first rack system we built. So here we have this is a rack server here, and then you just stack them together. And you put networking on the backside here. So now we have a kind of much nicer networking. The Centum was also a rack server, this rack-based system. It was the first 64-bit machine we had. So single core 64-bit AMD processor. And we have 210 of these. That's why it's called Docenten, with humor in the naming here. Also, gigabit Ethernet connected together to a large switch here. This is the system console where you kind of interface with machine when something is broken. The switch. In 2007, we got the IBM machine with blade chassis. So this is a blade chassis here. IBM blade chassis, and we got 256 machines with 4 cores, so we have over 1,000 cores in this machine. So it was the first time we got over 1,000 cores. But we still had gigabit Ethernet in this, so that's why we have a lot of cabling. And we also needed to have cooling, so the rear heat was kind of taken away using a heat exchanger, which we put on the back of the machine. This is the replacement of the series grid machine. Here we have Dell's blade machines again. And in the grid, data is important. So half of the machine is just disk storage. So all of this here is just disk, to analyze all the collisions in the accelerator in CERN. This is the Plato machine. We've got 20 teraflops in 2009. Alarik, I showed you before. Aurora. And if you want some more information, we have the Lunar webpage here. So we can start. If you have ideas for a PhD or master thesis work, we work. If you get a master thesis work on structural mechanics, we can probably arrange you to help out with your, so that you can access to these machines if you want as well. So if you have any questions on that, you can ask either Eric in structural mechanics, or ask if you have another supervisor, get in touch with Lunar and we can try to help out with that. So that was, I would like to have a 5-minute break, and then we can, I will show you how you can access, how it actually looks to log into one of these machines today, and how you can use the software on the machines. So let's take 10 minutes and get back 14:25. So you can see it's a multi-use machine, so there's a lot of users on the machine at the same time. So this is a shared machine. Another thing you can also look at is that you can look at the queuing system. You can type SQ. You see here that we have these are jobs running on the machine. This here is a node, Aurora node 27. So this is one server in our rack, and also this shows what job is running. So R stands for running. It has been running for 3 hours and 14 minutes. Here is a job that has been running for 4 days and 7 hours and 6 minutes and 15 seconds. So you see here there's a lot of jobs running at the same time. we can see how the machine looks like. So here is a listing of all the nodes. So here you can see 158 nodes are allocated running jobs. This is actual servers, so 158 servers running on the machine. And here is idle, means that this is a server not doing anything. And you have then we have different queues here. We have special queues for GPUs, for visualization, and so on. So what you do when you run it, you submit a job to the queuing system, and then it starts running. And I can do, for example, srun means that I want to run a command, but I don't want to run it on this machine I'm logged into, but on a node. So I can run the date command here. Okay. Specify that I'm. So now this command here told the system here, I want to run on the Elvis partition, which is part of 20 nodes here on a special account called Elvis test, and I want to run the date command. So now it went out and ran the date command on a certain node. I can also show here that host name that shows the name of the machine I'm running on. So now I was running on EGO1. It could be EGO2 as well, depending on what resources are available. I want to show you here that you can run, so for example, I can run Spider here. It takes us a long time to start on a supercomputer as well, so it doesn't scale very well on multiple processors. So this is Spider running on Aurora. And you can also, well, one other thing you can see here that the front of machine here, which is we are running on, you can see here that it has 20 cores, but it has hyper-threading enabled, so it has actually, you see, it's 40 processors running at the same time, this machine. Here you can also see the processors running. You can see the tasks here for each of the processors on this machine. But what about running our example from this course here? Does it show that it works fine? I think I can run it. So this is the well-known code here for groundwater simulation. Same code as I have on a Windows machine. Let's see if it runs. This is the demo devil here, of course. So let's see here. Okay, you have to. I will run it on the command line instead. So Python So you type Python to run your command, and then I have my so this is ground router flow. It's a bit extended example here, but basically you can run it here just like you do on a normal computer. You can see the geometry, the mesh, nodal values, element values. I can zoom in here and look at stuff like that. So running on Aurora. So that here you can see that Python works on all platforms. It looks kind of the same on all platforms. And so if you code well, it can run on any platform you decide. It's also possible on Aurora to run ParaView using hardware acceleration. So let's see here if I can do post-processing ParaView. So because this is a shared machine, you can ask for a node to run ParaView on. So in this case here, I request 30 hours of 30 minutes of compute time on a visualization node. And then I want to run it on a, let's see if it's available today. We can do 2 NVIDIA GPUs. And then I press start here. Now it executes this application on a separate node and brings up the user interface on my display here. So this ParaView is not running on the machine I log into, but it's running on a separate node in the system with hardware acceleration. So here I can do. So now I'm running this on a server with a graphics card installed. So here you can see you have quite high performance on the visualization parts as well here. So this can be run on a normal laptop, this desktop, and then you can access these tools without having access to any powerful computer at home. And if we look at the About page here on ParaView, you can see that it's running on NVIDIA K20. Let's see if we can see if we have some memory as well. But it has access to 96 gigabytes of memory here as well. And if you look at the queuing system now, you see here that I'm running here. This is running as a job on the cluster on node EG01. It's running. And then when I'm done with this, I can stop the program. And then it doesn't run in the queue anymore. So this is quite a powerful resource to, if you have a lot of jobs to run. For example, if you have a parameter study, parameter studies are what you call trivially parallelizable, because they don't need any communication. You can just send, for each parameter, you send one job, and then you send all of them at the same time, and they will execute at the same time and finish at the same time. So then you can do a parameter study of 30 parameters running on 30 servers, and they complete at the same time. So in that case, you have reduced your computing time by so you increase your computing time by 30 times. So that was what I wanted to show here. And if you have a master thesis work that needs computation, you can probably let your supervisor apply for time, and then you can get access to these machines. So that was it for today.